Yeah, you can start now. Yes.
Okay. So, hello everyone. Thank you so much for joining. So today we are here to introduce you to TinyLlama, an open source small language model. So the TinyLlama, next please. So we just quickly go through the introduction by TinyLlama. So as you all know that 2023 is the era of large language models. So besides the huge applications and the various potential use cases of LLMs, the LLMs which tend to have billion or even trillion of parameters require massive computational power and memory, and so not always suitable on mobile devices and edge computing devices. So here comes the TinyLlama, which address these issues by exploring the behavior of transformer decoder only model, but with only 1.1 billion parameters and trained on approximately 3 trillion tokens. So this size of TinyLlama is comparatively quite small as compared to the large LLM models whose size is with the 7 billions or even in the trillions. So with these few parameters, TinyLlama require very less computational power and memory to run, so make it ideal for deployment on mobile devices or edge computing devices. So besides this, the TinyLlama is also available as open source on Hugging Face, which promotes research collaborations and transparency within the researcher community. So next, we'll discuss about the potential use cases of TinyLlama. TinyLlama has a huge applications, but the major area is the first one is the edge computing, where TinyLlama can be used for machine translation, test summarization, local language processing, question answering without the use of the internet or where the internet accessibility is very poor. So the second one is the chatbot or virtual assistants where TinyLlama can be used to generate dialogues for customer service, education, or even entertainment. And the third one is the streamlined workflow, where TinyLlama can be used to perform several repetitive tasks, such as scheduling appointments, extracting any information from documents, or composing any routine emails. So go ahead with the training.
Right. So now we'll discuss how the TinyLlama model was pre-trained. First, we'll check what are the makeup of the pre-training data. So the TinyLlama model was trained on two distinct data sets. And this is a Slim Pajama dataset, which was derived from the original Red Pajama dataset. It was also retrained on the star coder data, which you can find on GitHub. So what makes up the Slim Pajama and what makes up the star coder data? In the Slim Pajama data, it contains natural language data, while in the star coder data, it contains mostly code data. And this data was split in a ratio of 70 to 30 to pre-train the TinyLlama model. So now that we know the data, what is the architecture of the TinyLlama model? So the architecture of the TinyLlama model resembles the Llama model architecture. And this Llama model architecture also resembles the original transformer architecture that was proposed by Bazwani in 2017 in the paper, Attention is All You Need. So what did they change between the original transformer and now the Llama, which was then used for the TinyLlama? What they changed is that they changed the positional encoding. And in this case, what they used is that they used the rotational position encoding. And also, they changed the attention. They used grouped query attention. They also changed the normalization. And in this case, they used the RMS normalization. They also changed the activation function. And in this case, what they used is that they used this swish and gated linear unit, otherwise known as swiglu, as the activation function. So what these changes did is that they made the model more computationally effective. Now we can move on to the next one, which is speed optimizations.
TinyLlama has three speed optimizations: fully charted data parallel, FSDP. TinyLlama integrated FSDP to leverage multi-GPU and multi-node setups efficiently. FlashAttention. TinyLlama integrated FlashAttention 2 on optimized attention mechanism, improving the compute performance. Xformers, TinyLlama replaced the fused Sweglue module with the original Sweglue module. This increased code-base efficiency, leading to reduced memory footprint. Next. In traditional distributed data parallel training, each processes maintain a full replica of the model's parameters. This can create a bottleneck, especially as the model size increases. Unlike traditional data parallel, fully sharded data parallel divides parameters all across data parallel workers. This assists scaling the training process across multiple computing nodes, leading to a significant improvement in training speed and efficiency. The tension layer is another bottleneck in scaling to longer sequences, as its runtime and memory increase quadratically in the sequence length. Attention 2 well exploits the asymmetric GPU memory hierarchy to bring significant memory saving, bringing down attention layer from quadratic to linear, and runtime speed up by 2 to 4 times compared to optimized baselines, with no approximation. No approximation in this context means it achieves its memory savings and runtime speed up without lowering its computational accuracy. Next. FlashAttention loads keys, queries, and values once, fuses the operations of the attention mechanism, and writes them back. Next. Xformers utilizes attention mechanisms to capture dependencies between different elements of input data. The ability to capture dependencies enhances the understanding of complex relationships. Attention mechanisms allow the models to focus on relevant information while ignoring irrelevant details. Multiple calculations can be performed simultaneously by breaking down tasks into smaller parts. It reduces the memory footprint, enabling the 1.1 billion model to fit within 40 GB of GPU RAM. Next. TinyLlama achieves 24,000 tokens per second per 140 GB GPU, and the bar graph 100 billion tokens. TinyLlama 1.1 billion comes in first with 3,456 hours. Pythia 1 billion model comes in second with 4,830 hours. MPT 1.3 billion comes in last with 7,920 hours. Next.
In this training section, I first introduce some model terminology. LeadGPT framework is a hackable implementation of a state-of-art open source large language model based on NanoGPT used for pre-training and fine-tuning and especially designed for speed. Autoregressive language model is a feed-forward model that predicts the future word from a set of words in a given context. Adam Double Optimizer is a stochastic gradient descent method with adaptive moment estimation and weight decay. Finally, cosine learning rate schedule gradually reduces the learning rate following a cosine safe curve with specified warm-up period and initial learning rate. Next. TinyLlama use LeadGPT framework employing autoregressive model with Adam W optimizer and cosine learning rate scheduler with 2K warm-up steps and small initial learning rate of 10 to the power negative 4. Next. In terms of size, TinyLlama is a small language model with 1.1 billion parameter that can literally fit into 550 MB of RAM with 4-bit quantizations. However, the model was trained with nearly 3 trillion token, which is approximately 100 times larger than that suggested by Chinchilla scaling law. The model was trained for 90 days using 16 NVDA A10040G GPUs. The training cost is approximately 150K, which is estimated based on cloud provider rate. Imani, you can go ahead.
Thank you. So now we should go through the results and see what the training of the TinyLlama yielded. So the TinyLlama, after training, was evaluated in three ways. The first way was using common sense reasoning tasks. Second way, its evolution of performance during training. And the third way was on the problem-solving evaluation tasks. In the common sense reasoning tasks, it was evaluated on tasks such as HelloSwag, OpenBook QA, Wino Grande, Arc Easy, Arc Challenge, BullQ, and Picker. For the evolution of performance during training, it was tested, it was evaluated using the common sense reasoning tasks and compared to a model similar to, with the parameters similar to it. In the problem-solving evaluation tasks, it was evaluated using the instruct eval benchmark. Let's look at the first task it was evaluated on, and that's the common sense reasoning task. Here, the model was evaluated against models that have similar parameters to it. In this case, OPT 1.3 billion, Pythia 1.0 billion, Pythia 1.4 billion, with that being the parameters that these models have. If you can look clearly, the zero-shot performance on these models, and particularly the TinyLlama model, showcased that the TinyLlama performed better than its compatriots on all datasets other than the Wino Grande and the BullQ dataset. And here you can see it was outperformed by OPT 1.3 in the Wino Grande and by Pythia 1.4 in the BullQ task. However, on average, it was the best performing model. During the evolution of performance during training, when it was evaluated against Pythia 1.4, it was clear to see that with more GPU hours, it was able to outperform Pythia 1.4 on all the tasks other than the BullQ task, which in this case showcases that it was performing better. And the last task, which is a problem-solving evaluation task, it was evaluated on the instruct eval benchmark. And this benchmark contains 4 tasks, and that's the MMLU, where there was a 5-shot, it used 5-shot, BBH with 3 shots, human eval with 0 shot, and drop with 3 shots. Here, it was compared against Pythia 1.4 and Pythia 1.0. In all these 4 tasks, it was able to perform Pythia 1.4 and Pythia 1.0 on all the tasks other than the MMLU task, where Pythia 1.0 was the winner in that case. However, on average, it was the best performing model. In summary, we can say that TinyLlama 1.1 outperforms models that are within its range, that is within the 1.1 billion parameter range, in both problem solving and also in common sense reasoning tasks.
So now we conclude the TinyLlama, which includes its strengths, weakness, and limitations. So next. So the main key strengths of the TinyLlama includes the first one is it's lightweight and efficient. It's require very less computational power and memory, so making them ideal for deployment on mobile devices or edge devices. Second one is the open source and accessible. So as it is available on Hugging Face, so it can be accessed openly. The second one is the cost-effective deployment. So, training and running TinyLlama requires significantly less infrastructure and financial resources, so making it accessible to individual researchers even. And the few cons of the TinyLlama is its performance trade-off. So it may not achieve the same level of accuracy as compared to the large LLMs with more billions or trillions of parameters. And the second one is the limited fine-tuning options. TinyLlama offers very fewer pre-trained versions and may require more efforts for customizing, fine-tuning to specific domains. And the limitations includes the first is the interpretability challenges. So in this, the understanding TinyLlama internal working require very advanced knowledge and techniques. And the second one is the domain specificity. So TinyLlama performs best on tasks similar to the data it was trained on. But when to use TinyLlama for specific domains, it performance might drop or require any additional fine tuning or training. So that's all about the TinyLlama. So thank you so much. Any questions and queries?